Something is moving inside Mars, not on the surface, beneath it. For years, scientists told us the red planet was frozen in time, geologically dead, seismically silent. But new data, decoded with the help of artificial intelligence, is quietly dismantling that story. A hidden layer of energy has been detected traveling through Mars in a way nobody predicted. A structure buried for billions of years has just been mapped for the first time, and a lake that once made headlines around the world may never have existed at all. 3 separate discoveries, 1 uncomfortable question. What else is buried down there, and why did it take a machine to find it? To understand why this matters, you have to go back to a moment nobody was watching. Mars Reconnaissance Orbiter has been circling the planet since 2006, quietly snapping images with its context camera, day after day, year after year. Nobody could manually sort through that volume of imagery fast enough to catch what mattered. So NASA's Jet Propulsion Laboratory built something to do it instead. A machine learning system trained to scan tens of thousands of black and white orbital photographs and flag one very specific thing: a fresh scar on the surface, a blast zone, evidence that something from space had recently slammed into Mars. What used to take human analysts months of tedious searching, the algorithm could do in a matter of hours. And in early 2025, it found something: a crater, 71 feet across, sitting in a region called Cerberus Fossae, more than 1,000 miles from where NASA's InSight lander had touched down years earlier. On its own, that might have been a footnote. One more scar on a planet covered in them. But here's where it gets worse. When researchers cross-referenced the timing and location of that impact with InSight's seismic records, they found something that shouldn't have been there. InSight had detected the shockwave from over 1,000 kilometers away. That distance is the problem. Scientists had built their entire model of Mars' interior on the assumption that the planet's crust would absorb and dampen seismic energy from an impact that far away, weakening it into silence long before it reached a listening instrument. It wasn't supposed to survive the journey. It did. Read that again. A signal that should have died out somewhere in the crust instead reached a seismometer over 1,000 kilometers away, strong enough to register clearly. Something inside Mars is carrying energy farther and faster than anyone thought possible. Researchers on the InSight team started calling it a seismic highway, a deep, efficient pathway running through the planet's mantle, allowing energy from distant impacts to reach across enormous stretches of the Martian interior with far less resistance than expected. This wasn't a fluke. When the team went back and applied the same AI-driven detection method to search for more impacts within a 3,000-kilometer radius of InSight, they found 123 fresh craters. Of those, 49 lined up with seismic signals already sitting quietly in InSight's data, previously unexplained, previously unattributed. 49 confirmed connections between something crashing into the surface and something reverberating deep inside the planet. Think about what that means. For years, the working assumption was that Mars's interior was layered in a way that would trap and muffle seismic energy near the surface, the way a thick blanket muffles sound. What the AI-assisted analysis exposed instead was a mantle structure efficient enough to transmit energy across vast distances with surprising clarity. That is not a minor correction to a textbook diagram. That is a fundamental rewrite of how energy, and by extension, heat, and by extension, activity, moves through the inside of a planet we have spent decades calling geologically finished. A planet that was supposed to be still is apparently very good at carrying a signal a very long way. And once scientists accepted that, they had to ask the next question. If seismic energy can travel that efficiently through Mars's mantle, what does that tell us about what the mantle is actually made of, how hot it still is, and how dead this planet really is? This is not chaos. This is structure. A structure that had been sitting there, undetected, for as long as humans have been sending spacecraft to Mars, because no one had the tools to listen closely enough or fast enough. And it took a machine sorting through tens of thousands of images, matched against a machine sorting through years of seismic waveforms, to finally catch it. According to the InSight team itself, this finding forces a reconsideration of a hypothesis that had gone largely unchallenged for years. What most people following space news are not seeing is that this isn't really a story about one crater. It's a story about what else might be traveling through that same hidden highway, undetected right now while we're not equipped to notice. But the mantle wasn't the only place where the underground story of Mars was quietly rewriting itself. At almost the exact same time, on the opposite side of the planet, another buried mystery, one far more famous and far more explosive when it first broke, was being pulled apart by a different set of instruments entirely. In 2018, an instrument called MARSIS, riding aboard the European Space Agency's Mars Express orbiter, picked up something that stopped planetary scientists cold. Buried beneath roughly a mile of ice at Mars's south pole, the radar detected an unusually strong mirror-like reflection, the kind of signal you get when radar waves bounce off liquid water rather than rock or ice. Water reflects radar back, almost like a flashlight hitting a mirror. Everything else absorbs it, scatters it, lets it slip through weakly. This was strong. This was clean. And on a planet where the search for life is inseparable from the search for water, that single reflection detonated a global conversation. Scientists proposed it had to be a briny lake, kept liquid despite the deep cold by a high concentration of salt lowering its freezing point. If true, it would have been the first standing body of liquid water ever confirmed on Mars. The implications for astrobiology were enormous. This is where everything changes, or so it seemed at the time. But here's where the story takes its hardest turn. Confirming a signal like that from orbit using a single radar instrument is not the same as proving it, and scientists knew it. For almost 20 years, follow-up observations using MRO's own subsurface radar instrument, SHARAD, had scanned that same region and found nothing conclusive at those depths. No strong reflector, no obvious confirmation. The signal that started the entire conversation sat there for years, unresolved, unconfirmed, impossible to either validate or dismiss with the tools available. Until engineers tried something almost nobody had used before on a mission this mature. They rolled the entire spacecraft 120 degrees over the precise target area, a maneuver that dramatically boosted the strength and depth of SHARAD's radar signal, letting it punch through the ice far deeper and far more clearly than ever before. What most people are not seeing is how rare that kind of maneuver actually is. Rolling a multi-billion-dollar orbiter nearly upside down over one small patch of a planet is not something you do casually. It reflects how seriously scientists were taking this unresolved mystery. And when the data finally came back, published in Geophysical Research Letters in November 2025 by Gareth Morgan and then Putzich of the Planetary Science Institute, the conclusion landed like cold water. The feature beneath the ice, they determined, is more likely a layer of rock and dust than a lake of liquid brine. Not water, not the frozen twin of an underground sea. Something far more geologically mundane, sitting exactly where a discovery of enormous consequence was once believed to be hiding. Sit with that for a second, because the emotional whiplash here is the entire point. One of the most exciting exobiology headlines of the last decade, a hidden reservoir of liquid water on Mars, spent years as a live possibility, shaping mission priorities, shaping public imagination, shaping the entire framing of, is there something alive down there? And an improved radar technique refined enough to finally see clearly, quietly close that door. But, and this is the twist most coverage buried, the scientists involved were careful to frame this as anything but a dead end. The same enhanced radar roll maneuver that disproved the lake also proved something else entirely. That this technique can now be used to hunt for genuine subsurface resources elsewhere on the planet with a level of clarity nobody had before. In other words, the tool that took away one discovery just handed scientists a far more powerful way of finding the next one. The lake is very probably not there, but the method that killed it just opened dozens of new places to look. And while that story was unfolding at the pole, a rover crawling across a crater floor near the equator was quietly uncovering something that had been hiding for over 3.5 billion years. Perseverance landed in Jezero Crater in February 2021 with one job: hunt for signs of ancient life. Everything about that crater's geology suggested water had once been there. Carbonates in the rock, the kind of mineral that on Earth typically forms in stable, long-lasting bodies of water like shallow seas or ancient lake beds. But minerals on the surface only tell you part of the story. The real history is written underneath, in layers you cannot see just by looking. So Perseverance carried an instrument called RIMFAX, a ground-penetrating radar mounted directly on the rover, designed to image the shallow subsurface as it drives, essentially giving scientists an X-ray of the ground beneath the wheels. Across 78 separate traverses of the crater floor between September 2023 and February 2024, RIMFAX peered nearly twice as deep as any previous radar survey of that terrain had managed. And what it found, more than 35 meters below the surface, was a delta, not a modern one. An ancient river delta, buried and preserved, formed somewhere between 3.7 and 4.2 billion years ago, sloping layers of sediment called cliniforms, the exact structure you'd expect, where a river once emptied into standing water, depositing sand and mud in stacked, sloped sheets over time. A team led by Emily Cardarelli at UCLA combined that radar data with satellite imagery and the rover's own GPS track to reconstruct a full three-dimensional map of these buried layers, published in Science Advances. And here's the part that reframes everything. This discovery pushes the window for potential ancient habitability on Mars earlier than scientists had previously mapped. Water wasn't just present at Jezero, it was present sooner and for longer than the existing timeline accounted for. Think about what that actually means for the search for life. Every additional stretch of time that liquid water existed on ancient Mars is another stretch of time during which, if life ever had a chance to take hold anywhere on this planet, the conditions might have supported it. A buried river delta doesn't prove life existed, but it extends the runway. It adds pages to a story we thought we already knew the length of. Now step back and look at what's actually happening across all three of these discoveries, because none of them are really separate stories. They are the same story, told in three different locations on the same planet. A machine learning system, sorting through tens of thousands of orbital images, found a crater that exposed a hidden seismic highway running through Mars' mantle, deeper and more efficient than any model predicted. An advanced radar technique, pushed to its absolute limit through an unconventional spacecraft maneuver, tore down one of the most famous discoveries in modern Mars science and replaced it with something quieter, but arguably more useful, a proven method for finding real subsurface resources going forward. And a rover-mounted radar, reading depths nearly twice as far as anything before it, uncovered a delta that had been sitting in silence for over 3.5 billion years, rewriting the habitability timeline of an entire crater. In every single case, the discovery was invisible to the naked eye and invisible to conventional analysis. It took radar to see through rock and ice. It took AI to sort through volumes of data that no human team could realistically process at the required speed. And it took an unconventional maneuver, an unconventional depth, or an unconventional cross-reference to finally catch what had been sitting there the entire time, waiting. According to informed voices inside the missions themselves, the InSight team explicitly describing their seismic highway finding as challenging a long-standing hypothesis, the shared team explicitly rolling their spacecraft to chase down a mystery that had gone unresolved for nearly 2 decades. The RIMFAX team explicitly extending the habitability window for an entire crater based on a single buried structure. The language coming out of these papers is not the language of routine confirmation. It's the language of models being revised in real time. That is what should actually unsettle you here. Not a single shocking image, not a single dramatic quote. The quiet, repeated admission across 3 independent instruments and 3 independent teams that what they expected to find beneath the surface of Mars was not what they actually found. And this raises the uncomfortable question nobody wants to sit with for very long. If 3 separate investigations, using 3 separate techniques, each independently revealed that our existing models of the Martian interior were incomplete or simply wrong, what does that say about everywhere we haven't looked yet with this level of resolution? Mars is roughly 144 million square kilometers of surface area. InSight sat in one location. Perseverance has traversed a few dozen kilometers of one single crater. The enhanced shared technique has only been focused on one polar region so far. The tools that just rewrote 3 separate chapters of Mars science have barely scratched the surface, literally, of the rest of the planet. This is where the power shift becomes obvious, even if it hasn't been framed this way in most coverage. For decades, human scientists set the pace of Mars discovery, limited by how many images a person could review, how many radar returns a team could manually interpret, how many seismic waveforms a researcher could sit and analyze one at a time. That pace is no longer the bottleneck. The moment JPL's algorithm could scan tens of thousands of images in hours instead of months, the discovery pipeline for this planet fundamentally changed speed. The moment researchers could cross-reference 123 newly identified craters against years of seismic data and find 49 matches, almost automatically, the scale of what's discoverable expanded past what any single team could have manually attempted in a comparable time frame. The bottleneck now isn't human analytical capacity, it's mission time, spacecraft availability, and where we choose to point our instruments next. And that reframes the consequences of everything you just read. If a machine sorting through existing archival images can uncover a mantle structure nobody expected, what happens when that same approach is turned loose on the full multi-decade image archive from Mars Reconnaissance Orbiter, rather than just the images near one lander's seismic range? If an improved radar roll maneuver, applied to a single polar target, was enough to overturn one of the most cited exobiology stories of the last 10 years, what happens when that same enhanced technique is systematically applied across the rest of the ice caps, or across the mid-latitude regions, where some scientists suspect additional buried ice or mineral deposits might exist? If a rover radar peering less than 40 meters into one crater floor was enough to extend the habitability timeline of an entire ancient basin, what does a future rover, or a future orbital-scale radar survey with even greater depth penetration, stand to find in craters we haven't even prioritized yet? None of these are hypothetical exaggerations. They are the direct stated implications of the papers themselves. The shared team said outright that their enhanced technique can now be applied to search for subsurface resources elsewhere on the planet. The InSight team said outright that this seismic highway finding challenges a long-standing hypothesis about how energy moves through the interior of Mars. The Jezero Delta team said outright that this buried structure extends the window for potential ancient habitability beyond what was previously understood. Each of those statements, on their own, is a controlled, careful, scientific admission. Stacked together, they form something much larger, a pattern of a planet that keeps turning out to be more layered, more active, and more historically wet than the models built before these tools existed ever accounted for. So where does that leave us? It leaves the story of Mars in a strange, unfinished place, not resolved into a clean answer, but cracked open into a wider set of questions than existed before any of this data came back. We now know energy moves through this planet's interior in ways that contradict the standard model. We now know one of the most famous discoveries of the last decade likely wasn't what it appeared to be, and that the very method that disproved it is about to be turned on the rest of the planet. We now know at least one crater carries a hidden 3.5 billion-year-old river system nobody could see from orbit or from the surface with the naked eye, one that pushes back the earliest window we thought life might have had a chance to take hold. Every one of these findings came from beneath the surface. None of them came from looking at what's obviously there. All of them came from tools, radar, seismometers, and increasingly artificial intelligence, built specifically to see what human eyes and human patience never could. Which leaves the real question sitting there, unanswered and probably unanswerable for a long time yet. If 3 independent instruments pointed at 3 separate regions of Mars, each independently forced scientists to rewrite part of what they thought they understood about this planet's interior, what happens when we finally get the resources, the mission time, and the AI-driven analysis pipelines needed to look everywhere else at once? What is still sitting there in the other 99% of this planet we haven't scanned this closely, waiting for the right instrument, the right maneuver, or the right algorithm to finally notice it? Nobody currently working on these missions can answer that, and maybe that's the most unsettling part of this entire story. Not what we've already found beneath the surface of Mars, but how much of it we still haven't even looked for.